Thank you. So first of all, thank you for the kind invitation. So in this section, you are going to see, I guess, 3 talks which are related with photonics experiment. And since we are a broad audience, I will spend the first part of my talk to introduce you our platform. Then we will start seeing how you can carry out classical machine learning to optimize quantum hardware. And then only in the perspective, we are going to see something to do in the quantum domain. So to briefly provide you the framework of our experimental contributions, we have been working in quantum information in the last 20 years, and in the last few years, we devoted attention to implement quantum information on a chip. So this is because when you want to scale up your technology, you then face some problem of size, stability, cost, and so on. So in particular, our approach is a strong collaboration between Sapienza University in Rome and Politecnico di Milano in Sener, where we adopt laser writing technique to fabricate waveguides which are inscribed inside the substrate of glass. So the basic principle is that you would like to generate, manipulate, and detect light inside a single component. And to this purpose, what you can do, you can take a component, in this case a glass, you slightly focus a laser inside the glass, and if you adopt a powerful laser with appropriate characteristics, you can fabricate a waveguide which is inscribed inside your device. So this video shows you a bit how you carry out this laser writing technique. You have a substrate of glass, you have a telescope, a laser coming from the top, you focus the laser, and now you can see a white spot, and this white spot is the plasma, which is inducing the change in the index of refraction of your material. So this is very similar to the technique if you go to Colosseum in Rome or Tour Eiffel in Paris, you can buy this gift where you see Colosseum inside the piece of glass. So that's the same techniques, but much, much better control. Because in that case, you have a control on your fabrication facility with a resolution of dozens of nanometers. So the advantage of this technique is that you can very easily fabricate a prototype, test it, and then proceed in the technology development. So it is suitable in this medium-term goal where you don't want to scale the facility, but you want to have new building blocks that you can then adopt to carry out quantum information processing. So this is a bit a summary of the components that we developed together with Milano in the last few years. So the first starting point was a beam splitter. Very easy. You take 2 waveguides, you browse the 2 waveguide closer, and you get a coupling via the evanescent field. Then we carried out some integrated logical gates, like a control node gate that could work in post-selection by exploiting the nonlinearity induced by the measurement process. Then we started carrying out more complex apparatus, like this one, where you have many beam splitters which are concatenated. You have many phase shifters. In this case, you have something like 100 components, and this allows you to implement a quantum walk via photons that evolves inside an integrated photonics chip. Then we could also integrate other optical components, and all these devices were fixed. Once you fabricate your device, your dynamics is established during the writing process. So more recently, we introduced a kind of reconfigurability of your device, which is something that you already have in other platforms, but the reconfigurability was missing in this photonics platform. In that case, you have the waveguides. You can, in this case, fabricate a thermoelectric controller on the top of the waveguide, and then by locally heating close to the waveguide, you can change the index of refraction. So in 2015, we implemented the first device with this kind of technology. Then we scaled up this from 1 to 4. In this case, we could carry out a test on the foundation of quantum mechanics on a chip, specifically quantum contextuality. Here we developed a kind of programmable simulator where you could have different chip, phase controller, and more advanced arrangement. And more recently, we just reported a source of photonic entangled pairs which adopt this kind of technology. In that case, you can generate a pair of photons at the telecom wavelength inside this nonlinear crystal, in which you have written waveguides by laser writing. This is only to provide you a kind of building blocks that we can put together. And then finally, when you do this laser writing technique, you can also move your chip up and down. This means that you can fabricate waveguides not only with a planar geometry, but you can also have a three-dimensional geometry. And then we implemented a treater. A treater is a generalization of a beam splitter from 2 modes to 3 modes. You have 3 modes in, 3 modes out. And you can do that, in this case, using this 3D layout. Then you can have more funny architecture like this one, which is a fast Fourier transform of 8 modes, which go up and down, left and right, and you have beam splitter along different directions. This is a kind of variant of this one. And we also could implement, by using the 3D layout, you can fabricate some structure, and you can carry out some kind of quantum simulation which exploits this 3D layout. In this case, we implemented a quantum maze, and we investigate what is the efficiency of a worker to escape from the quantum maze when you have no noise, and when you increase the number of noise. This is a way to investigate experimentally how quantum transport is affected by noise during the evolution. So this was a bit only to provide you the photonics perspective from our contribution. And now, what is the topic of the goal? The first step that we have been undertaking in the last couple of years is to try to exploit classical machine learning to obtain new insight into quantum engineering. So our goal has been mostly to generate data from a quantum device and to exploit, I would say, more simple machine learning methodologies to certify and identify the underlying structure of the quantum system. So we have a quantum data and a classical analysis. And today, I will focus on 3 subtopics, especially on the first one, which is the goal is to validate a quantum photonics platform, specifically Boson sampling. Then the second one is how to extract information for quantum metrology. I will not have time to focus on that. And then finally, how you can learn quantum state, where learn is not in the physical meaning, but more with a computer scientist perspective. Let me add that on these topics, Iris Agresti will give a talk in half an hour. On this, there is no. Then you have a poster by Tyra Giordani, and on the last, you have also a poster by Davide Poderini. So I will only briefly mention these 2 experiments, but you can certainly discuss with my collaborators these 2 topics during the poster session. But now I would like to focus on the first part of the talk, which is the validation of quantum technology. And specifically, I'm going to focus on the photonic scheme, which have been more discussed in the last few years, which is Boson sampling. So since the audience is larger, I would like to briefly introduce the topics to identify what is the key point from our perspective. So Boson sampling was introduced, I will say, in the quest of the so-called quantum supremacy regime, or according to the last few months of discussion, quantum advantage, because it's more scientifically sound. But let's say we can say that the 2 sentences have the same meaning. And the goal is to experimentally demonstrate a regime in which quantum technology can outperform classical technology, at least for a given specific task. And within this framework, Arkhipov and Aronson have proposed to exploit boson sampling. So what is boson sampling? It's the following problem. You have n bosons, let's say photons, which are indistinguishable but not interacting. You let the n bosons evolve over an array of m optical modes, where m is much larger than n. These m optical modes are highly interconnected, but in a random way, so to avoid any symmetry in your evolution. The bosons evolves. This is a random structure. It's random, but you know the structure. And your goal is to sample from the output state. You don't want to calculate the output state. You want to sample events which follow the output distribution of such a dynamics. And this is very similar to the random quantum circuit, which is today followed by Google. And we say that random quantum circuits was inspired by the Boson sampling approach. So you can ask yourself, can I address this problem with a classical hardware? Is it efficient, the solution? And the answer is no. Why is no? Because that's the answer by Arkhipov and Aronson. You need a 95 long paper to really understand where the hardness is coming from. But if you want to identify one key point of the hardness, it's the boson's indistinguishability. If you have n bosons which evolves according to unitary transformation, and you want to calculate the output state contribution, you need to calculate the permanent of some squared matrices of dimensions n times n. And the permanent of a matrix with complex coefficient is something very hard to calculate if you have a classical approach. It's not only hard to calculate a permanent with complex coefficient, it's also hard to approximate a permanent with classical complex coefficient. And this was the main result by Aronson and Arkhipov. So this slide on one sentence is, this is hard classically because the complexity is going exponentially. And this lies really at the heart of computer science, because otherwise you will have some very unlikely event that could occur. Then you can ask, what about a quantum hardware? And then you can ask, okay, I will try to address Boson sampling simply by having a Boson sampler machine. So what is a Boson sampler machine? It's a machine where you have n photons. The n photons are indistinguishable. They propagate over m optical modes. This is a box that must implement your unitary evolution u. And then at the end, you will need to detect the output state. So your goal is to have the photons on one side, the evolution, and the detection. If you want to implement a unitary transformation in optics, this would correspond to a very highly complex interferometer. And this is where integrated photonics is entering in the game. You are going to implement this huge interferometer by exploiting integrated photonics. This is because if you have a unitary transformation acting on m optical modes, you can decompose this structure as a polynomial number of beam splitter and phase shifter. In this case, what you see is a 5 modes interferometer. So this is now your unitary transformation. And the unitary transformation, depending on the unitary transformation, you will need to change the reflectivity and phase of your device. So this was a big picture, but I would like at least to bring you a picture of what is Boson sampling. So I would like to show you with this video what means doing Boson sampling in the lab. Obviously, it's a simplified apparatus, but really to get you an intuition of what's going on. Poisson sampling means you first want to have single photon states. In our case, we generate single photons by generating photon pairs. You take a pulsed laser, you excite a nonlinear crystal, and you create some pair of photons. In this case, we create 4 yellow balls, which are 4 photons, via 2 pairs generation. That's the pulse, you create the photons. You take 1 photon here as a trigger, while the following 3 photons are injected in 3 single-mode fiber. You have now the 3 single-mode fiber, but you want your photon to be indistinguishable. This means you need to synchronize the photons in all the degree of freedom, time, frequency, polarization. In this case, you have some delay line which allows you to synchronize the wave packets. Then you can go on other 3 fibers. These go on a fiber array. The fiber array is connected with your chip. You will have light evolving in the chip, and that's where you will have the unitary evolution of your system. In this representation, you will see a 13 modes device. Okay, you see the photon splitting, which is a way to convey the message of the quantum superposition. Don't take it seriously. Then you have on the output 13 output modes, which are connected with 13 fiber mode array. You have then your single photon detector. And then what you do, you run your experiment many times. each time you run the experiment, you will measure a different output state, and this is Boson sampling. You are generating events according to the output distribution. So in that case, you have 3 photons over 13 modes. So your sampling event is a string of 13 bits, 10 of which are 0 and 3 are 1. And then you repeat your experiment many, many times. You have to do also electronic coincidence. You acquire your data, and this is what's coming out. And this is Boson sampling. Obviously, this is a simplified picture. If you go on the lab, it gets more complex. Boson sampling has been done by several groups in Europe, also out of Europe. And this is our approach, where you can see here the chip and the fiber array in and out. So in that case, you can see the results. You have 3 photons propagating over 7 modes, 3 photon 9 modes, 3 photon 13 modes. In this case, this is a small-scale Boson sampling. So your Hilbert space has dimension 300, and so you can measure the output probability. So the blue has experimental data, the orange has the theoretical one, and you can find a pretty good agreement. But somehow this picture of Boson sampling is not the right one, because here, in this case, you can see the probability patterns. But if you imagine to have 10 photons and 200 modes, your Hilbert space becomes huge. You will never be able to measure the probability. You will only see a string of 1 and 0. So you have some data pattern, but where you don't have the probability to see that your device is behaving properly. And now you have the question where machine learning may enter in the game, how you can characterize the output data of this device. So this is a bit a summary of the Boson sampling status of the art, where you have not only our contribution, but also contribution from other groups all around the world. So the first paper dates to 2013. You have other experiments. This is a chip from Bristol that you will maybe see in the next talk, or maybe not. You have this is the last Boson sampling done in China by the group of Jianwei Pan, where they had single photon sources based on quantum dot and 8 modes evolution. And then, obviously, what is the goal? You want to increase the number of photons, you want to increase the number of modes. And now what the question that pops up at the end is when you will increase the complexity and you will get a very large Hilbert space, how can you characterize that your device is behaving properly? Because Boson sampling is not only hard to simulate, to perform, it's also hard to verify. And this problem of validation, of certifying your quantum device, is not restricted to Boson sampling. It's common to any approach to quantum supremacy, from Boson sampling to random quantum circuits and also to quantum simulation. And so what you need to do is to develop different methodologies to validate, certify the output. Likely, you will never get the final answer. So if you factorize 21, you get 7 and 3, you can check that the answer is correct. In that case, you will only have a growing evidence that you are performing indeed the right task. So in the last few years, we implemented different approaches to validate the output state. And one could simplify this test in 2 categories. You can have some physical approach and some computational approach. The physical approach is try to look to the physics and to see whether the physics is behaving properly. For instance, you could identify some structure which allows you to demonstrate that you have genuine and photon interference. On the other side, you can have some computational approach where you take your output data and you exploit this as a pattern and you try to validate the pattern using different computational approaches. Computational approaches that could become more sophisticated and that could provide you stronger evidence. When you deal with this validation test, you also have to take into account the efficiency of your computational approach. Some approach may not be efficient in the sense that you need to calculate the permanent, while other one could be efficient. So I would like to focus only in the last 2 contributions that we carried out. The first one will be discussed by Iris Agresti in 35 minutes, so I'm not going to go into the details. This is a joint collaboration with Nathan Wiebe from Microsoft, and in that case, we validated the output via some kind of pattern recognition technique. Wait and you will know more. The second one is discussed by me now briefly, but more in details by Tyra Giordani in her poster. And this was just published 1 month ago. It's again a collaboration with other groups on the experimental side and on the theory side. And what we have been looking for is to identify some statistical signature of many-body quantum interference. So the original idea was the theoretical proposal, to be more precise, was published by Andreas Buchleiner from Freiburg and collaborators. And their goal was to try to identify in this output pattern of a Boson sampling some statistical signature which allows you to identify whether you are observing genuine quantum interference independently from your unitary evolution. And to perform this task, what you need to adopt, you need to evaluate the statistical moments of 2 modes correlation functions. So you measure your output state, you characterize the 2-mode correlation function, in particular in this case by exploiting the coefficient of variation and the skewness. And what you can see here is that depending on your particle, all your different evolution, all the different points correspond to different dynamics with cloud in different space. So what you can see here is that you can have some kind of classification of your different particles. So interesting aspect of this approach is that you can then exploit random matrix theory, and you can then perform this classification without the need to calculate the permanent of your unitary evolution. This means that this approach can allow you a validation which is efficiently from a computational perspective. So in that case, we performed this experiment. Again, we have 3 photons. In this case, we have a 7-mode evolution. You need to measure all the possible states where you have 3 photons on separate modes or also 3 photons together. This means that on the output, you need 21 detectors, and you need to measure all the possible correlation between the output detector. So in this case, you see the probability of the different 84 output states. Here, you can then estimate the correlator data set, and then you can do some pattern, some classification of your dynamics. So in that case, your main goal in this validation of Boson sampling, the goal that we have mainly undertaken, is to be able to validate the case in which your particles are indistinguishable versus the case in which your particles are distinguishable. And this is the result that you observe in the following plot, where you have on one side the dynamics that you obtain with indistinguishable particles, on the other side the dynamics that you obtain with distinguishable particles. And now you can exploit, in this case, machine learning as a proper tool to properly classify your experimental results. So we adopted these techniques. It worked properly. A key point is that this technique, I repeat, is efficient from a computational perspective. The number of samples required to perform this analysis was something like 2,000, 20,000 events, which is a reduced request in terms of running time for your experiment. And then as follow-up, we also tried to identify which were the most appropriate properties of this data set to validate Boson sampling. And to this purpose, we adopted a random forest classifier to test different features of the output distribution and to identify the feature which was more efficient on discriminating between these different hypotheses. So this, in the summary, if you want to have more details on that approach, you can refer to Tyra's contribution in the poster session. But the underlying message is that one can then apply machine learning with a growing complexity as a tool to investigate and validate quantum hardware in a regime where you have a data set which is pair, and then you need to be able to identify some underlying features of your output dynamics. Now, this was the first domain in which we adopted this technique. I'm now only very briefly quoting another experiment that we carried out, where the goal was to have adaptive single-shot phase estimation. And here, our goal was really to say we want to perform a very small number of experiments. We want to only send 20, 30 probes, and we would like to maximize the information that we can retrieve on a phase only by using 20, 30 measurements. And we want, in this regime, to try to saturate the information that we are able to extract from a system. This is typically the opposite side versus a typical quantum information experiment, where you are always not interested on how you achieve the saturation, but you only work in the regime where you have a very large number of samples. So in that case, we adopted an adaptive single-shot phase estimation, and we tried different techniques. The first technique that we tried is a recent proposal by Sanders and co-worker on particle swarm optimization. So in that case, what you do, you offline calculate the best strategy to estimate your phase. You elaborate this strategy before. It's an adaptive strategy. This means you measure the photons, and depending on the output, you decide what's the next measurement. So we implemented this device, but then we adopted other Bayesian inference approach, a Gaussian optimal approach, and also particle gas heuristic. And then we provided a comparison between these different techniques, also in noisy conditions. There is no poster on that, but I will be glad to provide you more information on that. So in this case, we had only single particle measurement. We had no null states. And now we are working on the following step, where we try to use null state as resources, and where we are now aiming to carry out not single parameter estimation, but multi-parameter estimation. And now the third topic that I quoted before is also to show how we can try to combine different techniques of machine learning to optimally extract information from your experimental set. We experimentally tested a recent proposal by Scott Aronson on the learning of quantum states, where by learning of quantum states, the meaning of this sentence is based on a training set of M measurements to predict new measurement outcomes. And this via a PAC learning approach, where PAC stands for probably approximately correct. So you have a learning state, you perform some measurement. Based on this measurement, you have some estimate, some guess, and then based on the guess, you can then make some prediction on other measurement. And the interesting part of this contribution is that with a PAC learning approach, the number of measurements that you need is not growing exponentially with the number of qubits, but it's growing polynomially. And this makes a huge difference. This means that if you don't want really to predict everything perfectly, but it's enough for you to predict almost all the measurement, almost in a reasonable way, you can really relax how many measurements you need to perform on your apparatus. So we implemented this experiment with a system up to 6 qubits. This is the number of measurements that you need to perform, and we, as predicted by the numerical simulation, could observe a linear trend, even in that case it's clearly limited to a small Hilbert space. So I'm close to the end. Now only to comment what's the next step. So in that case, the machine learning was on with a classical approach. Now the next step on which we are working is really to try the quantum machine learning. So we are working on two different kinds of apparatus. One which is based on a quantum walk, based on orbital angular momentum. Another one is something where you have two kinds of chip. One chip is programmable. So this first device generates some kind of dynamics, and the second apparatus aims to have some kind of iterative learning, but where you use a unitary estimation procedure. So thank you for your attention. And before the question, I would like to advertise a call for paper. You also add on your bag a small advertisement on open quantum computation and simulation, where I'm a guest editor also with Peter Wittek and Emanuele Della Torre. And the goal of this special issue, which is focused on quantum computation and simulation, at variance with other approaches, really +1 as a policy to somehow push towards an open policy of science. So in that case, the goal is not only to publish paper, but the goal, let's say the vision, is also to try to publish open source tools in a way to have a kind of shared approach in this domain. So that's where any of your contribution is very welcome, and we will get to provide you more details during the coffee break if you want. But again, I would like to stress that it's not only focused on open software, but that's where this special issue would like to bring a new spirit in our community. So thank you very much for your attention. Yes.
Hello? Poisson sampling, you have to control the phase of each arm, right?
Yes.
And is it done, or is it just randomly distributed? How do you deal with that?
So up to now, during the fabrication stage, the experiment that we performed in Rome, during the fabrication stage, we decided the geometry, the unitary transformation, and we fabricated one chip for one unitary. Anthony, in Bristol, they performed some Boson sampling, I'm advertising in the next talk, where they could reconfigure the device. So they could decide unitary transformation and then implement it. We are working on this with our platform, but we are not yet there.
In that case, finding out the control parameters for the phase becomes another very harder problem, isn't it?
So in that case, we are also working on how to use machine learning to deal with the chip. So that's the kind of dynamics where you have many parameters which control your device. And obviously, it's a number of parameters which control your device in a strongly interconnected way. To characterize this device requires some fancy analysis. And that's, again, something, but this is something that you can perform with classical light. This means that you can sight the light beam inside, you can measure the output pattern, and then you can use a kind of classical optimization algorithm of your phases. But I agree that this is not trivial. When the system is getting larger, you really need to work on that from an engineering perspective.
All right, okay. Thank you very much.
Thanks.
Okay, we have time for a second question. Any takers? Well, if not, then we can proceed with the next talk. Thank you.
Thanks.